Hello friends. So welcome you all to the AMBA development course session 32. In this session we are going to be covering AMBA architecture. Okay. So this is different from whatever we have discussed so far. This is about the bus interconnect. Okay. Within a chip. So we will be covering some overview of what AMBA architecture is all about, and then I will show you a sample structure of an AMBA architecture along with ARM processor in it, and then we will go into the details of AHB and APB bridges, APB bus, and what are the transactions and signals. And then APP bridge also is one of the modules related to the AMBA architecture. So before we jump into this discussion, I would like to give you some overview. Okay, what is this specification and why it was designed by ARM? This is the interconnect standard from ARM. Okay. So what was the motivation? How does it help in our design of an SoC which is ARM based? So let us look at the introduction part. AMBA is an acronym of Advanced Microcontroller Bus Architecture. This is a de facto standard for on-chip communication. So what is the de facto standard? Suppose you have ARM core, and then when ARM designed this processor, and then their business model was to give ARM as an IP, and then they also gave other IPs like cache controller, right? And then MMU, MPU. Okay, these are all something which is these models are going to be in the SoC, final SoC. Okay, and then SPU. So they designed different cache controller. Okay, so this will in turn will be giving instruction and data caches. So they designed all these modules as an IP. Now, having given this, if there is no uniform way of connecting them all together, okay, then there will be an issue, because the performance and power as well as cost, everything that we gain using these modules, okay, will be achievable only when we have an interconnect, okay, which is well designed and meets the requirements of the low power design that ARM is targeting. This is the low power chips, and for the applications, low power applications, the mobile applications or tablet and any other embedded low power devices. So the target market is this kind of a environment, okay, this kind of a product. So it is not enough if only these IPs are given, but there should be some standard interconnect also defined along with these IPs. Then it will be easier for people to buy these IPs and build their own IPs and interface with the rest of the items or modules in the IP. So this bus architecture was a de facto standard. What does it mean? It was originally designed for the use of ARM, only with ARM, and it was later on made as an open standard. Okay, and it became a de facto standard that any It's not that this is the only standard. There are other standards from the components too. But for the ARM products, ARM modules, the AMBA architecture specification is an open standard, which can be used not only to connect these which are coming from ARM. People can build their own IP and interface it with it. So that's the way this market grew unprecedentedly. So this SoC, making an SoC with this interconnect along with these chips is modules is what is the aim for coming up with this standard. So the low power design and the performance in terms of, when you say when bus is there and then we are talking about performance, is the bytes per second. Okay, how much of bytes can be transferred over this per second? That's one, that is bandwidth, okay, of this bus. Another one is a latency. That is, suppose memory MMU is connected to memory, okay, and memory is of course connected to the bus. If it is on chip memory, okay, then it could be an interface could be there with the bus and then connecting to the off chip memory. Now latency is what, when any address is sent out, okay, by the processor, how long does it take for a, maybe for a read cycle, how long does it take for getting the data back from memory to the processor? So this is the latency, and how fast any data can be transferred over the bus is what is bandwidth, and how many devices that could be connected to this, okay, to the bus. That is another design capability. So if there are some limitations on number of modules that could be connected to it, then there will be some limitations, right? So how many can be connected, that is how adaptable or how easy it is for people to build their IP and connect it to their bus without impacting the performance of code. And then what are the features are supported, okay, in any bus communication. As I told you earlier, that there could be one master at a time, but it doesn't mean that only ARM can be a master in the whole bus. Okay, there are other IP like a DSP processor could be sitting, and then that could be a master for its own transaction on the bus, and ARM could be one, and then there could be a DMA who is initiating the transfer between maybe peripheral to memory. So this kind of multiple masters could be there in the system. So this design should support multiple masters being in the system without competing. They will all be competing for the bus ownership, but it should be controlled by somebody. Okay, there should be some control logic in the bus for them, for the masters, multiple masters connected to the bus to transact over the bus. So that should be a facility. So maybe arbiter is one, which I will talk about later, but just to give you an overview, an arbiter is the one who decides among multiple masters connected to the bus, okay, who can own the particular bus, the bus for a transaction at a particular time. So what I am saying is maybe time t0 to t1, ARM can transfer over the bus, and then from t1 to t2, maybe DSP processor who is on the bus can transact over the bus, and then later on maybe DMA transfer could happen. So who decides who is the master at a particular time? Arbiter. That is the logic, which is a centralized arbiter who is the module is connected to all the masters in the chip, and then there is only connected to two pins, okay, two signals. One is a request and another one is grant. So every master who can initiate transaction over the bus are connected to the arbiter, and then they communicate to the arbiter before they transact over the bus. That means they should be granted access to the bus and they do it. So that facility should be there, and then there should be if you recall the non-sequential access, sequential access that we saw for the while talking about memory interfaces and different instruction, how much time they take, we say that okay, one non-sequential cycles and few sequential cycles. So that means what? Burst transfer, burst transfer should be supported. That means the initiator gives one address. Okay, that means address is first address is given, then the subsequent accesses are all to the address relative to this. Okay, if the bus width data width is maybe 4 bytes, okay, then plus 4, every address plus 4 will be transacted. That means multiple bytes, multiple words over the bus starting from some address. So that is a burst transfer, that is called burst transfer. And then there will be a split transaction. That means when we have multiple masters trying to transact over the bus, one option is to say that okay, one master communicates and then it finishes, and then next master communicates with whatever slave, and then it communicates with transaction. Another one is each master initiating some transaction, and then maybe this initially it was initiated, then this gets done for some time, then other master gets the bus and the data gets done. So the transaction is split across multiple cycles. So split transaction, that is another feature of a bus. So maybe that is another feature that would help in making sure that the bus is always utilized, because whenever any memory is to be accessed, it will take its own speed time for decoding the address and then coming up with the data. So during that time, those cycles, maybe some other master can be allowed to use the bus to initiate some other transaction. So maybe it may be with the peripheral, or it could be with some other external memory. So the same memory is not involved. In that case, maybe we can parallelize the transaction that is happening on the bus. So split transaction, bus transfer, and then low power. So there should be some features which is part of the bus to handle the low power design. That means these transaction over the bus do not consume more power, or when there is no transaction, the bus is not consuming power. So these kind of different features are built into this SoC, this particular AMBA architecture, and then released for that to be used within the SoC. So please remember, this is not outside the SoC; it is within the SoC. You might have heard about so many other bus standards like multi-bus or ISA. Okay, ISA in the PCI world, you would have seen that. Okay, PCI. Okay, peripheral component interconnect, and then multi-bus. Okay, what are the difference between these bus standards and what we are seeing here, or we are going to see here? The AMBA bus is within the SoC, that is within the chip, whereas the multi-bus, ISA, and PCI, they are all over the racks, maybe different, or PCB. Okay, within the PCB on the motherboard, you can see that ISA and PCI standards are there. We plug in some PCI based add-on cards to communicate with the motherboard of the PC, or a multi-bus is something like backbone. Okay, kind of a rack. Okay, so back plane, there are bus, address bus, data bus, which goes on the back plane, and then the cards go into the rack. So this is kind of a multi-bus standard, which is really which was given by Intel. So these standard bus standards were for either PCB or backplane kind of an environment, whereas AMBA standard is for within the SoC, system on a chip. Hope this introduction gives you some overview of what we are trying to do in this. Okay, now This is for the connection and management of functional blocks in a system on a chip. Okay, it is connection as well as management of the functional blocks modules. It facilitates right first time development of multiprocessor design with a large number of controllers and sensors. So the SoC what we are trying to build using this standard is not limited to one or two. Multiple peripherals could be there, controllers could be there, multiple processors masters will be there on the chip, and the AMBA architecture is adaptable for such a complex design, and it should be easy and it should in fact work first time. So to enable this, there are some features provided along with the AMBA specification, the testing feature. Okay, you could test any module independent of other modules in the system in the SoC and then interface it with the rest of the chip. So testing also is part of the design specification, and there are features available supported in the AMBA architecture. So AMBA promotes design reuse. That is very important because anyone designing a graphics processor maybe which is AMBA compliant, okay, graphics processor, then it could be used not only in one particular company's SoC. This could be sold to different vendors and it could be part of different SoCs. So since the interfacing is follows AMBA standard, any SoC which follows AMBA standard, this SoC could be reused there without any problem. It's like a plug and play kind of a scenario. So that design reuse is the most important thing for the quick adaptation of this particular standard for the SoC design. Wide adoption of AMBA specification throughout the semiconductor industry has driven a comprehensive market for the third-party products. So that's what I am trying to tell you. The design reuse helped in getting different third-party IP products which are AMBA compliant. There is plenty of IPs coming from different vendors which are AMBA compliant because there are lots of solutions which are ARM based, and these IP products can be integrated with them without any issue. So it actually helps in coming up with a different SoCs with the multiple features, and the SoC vendor also, the semiconductor company, can differentiate their design from other competitors by integrating their own IP as well as third party IPs which are AMBA compliant, and then follow the AMBA specification for interfacing or connecting the multiple modules within the chip. So this helps both the buyer as well as the vendor for a quick market time to market as well as easy to integrate, and then development is easier and testing is easier because all the features are there. So this has enabled availability of good support for the development of AMBA based. It's a good support in the ecosystem. Okay, that is very important for any product to be successful in the system in the market. So good ecosystem was developed around the AMBA specification. Now, what are the IP reuse related advantages? IP reuse requires a common standard while supporting a wide variety of SoCs. So there should be a common standard, but it should not be restrictive. If it is restrictive, then too many people may not be willing to use that. So the common standard allowing multiple variety of SoCs, supporting this wide variety of SoCs is the most successful feature of AMBA specification. So with a different power and performance area required. So SoCs with a different requirements. See, you may be interested in building an SoC for a 16-bit microcontroller for a very high, very low power design, low power environment. Maybe aeronautics, or maybe it is for a small embedded system. Okay, some pacemaker or something like that. Okay, or it could be a big router with a powerful performance requirement. Okay, the high power performance requirement in SoC could be big. So the AMBA specification should be generic enough for either for a very low end 16-bit or even 8-bit controllers, as well as 32-bit or 64-bit big process, systems. So and high performance. So this kind of these two are very wide requirements, right? But AMBA specification needs this, so that's why it is successful. And AMBA is a coherent hub interface. Is another standard, AMBA 5 interface. That interface extends performance and scalability to many coherent processors. So it is not even restricted to only single processor environment. Even multi-processor environment, this PHI, next level of specification of AMBA, helps you in having multiple processors in the system. Okay, cache coherency, and then multiple processors will have its own cache, L1 and L2. Maybe L2 cache may be common, then there should be cache coherency built into the product. So those kind of features are to be supported. So the CHI takes care of that. And multi-layer architecture acts as a crossbar switch between masters and slaves in AMBA 3 systems. So multi-layer systems in terms of area. Okay, when you have the interconnects going over multiple layers, the effective area occupied by the bus comes down, and the width of the bus. See, actually this AMBA bus varies in terms of width from 8 to 1024 bits. Okay, the data bus width of the AHB bus could be varying from 8 bits to 1024 bits. This is a very wide support in terms of number of data lines in the bus. So if we need to support this without sacrificing on the area as well as signal integrity issues, there should be some design kind of multi-layer architectures which will help you in terms of achieving the speed that is required for meeting the performance, and without sacrificing on the area or the noise on the bus. So reliability of the system will be better when you increase the speed of the transaction over the bus. So there should be some design elements built into the system. So that is also there. So the parallel links allow the bandwidth of the interconnect to support the peak bandwidth of the masters without increasing the frequency of the interconnect. See, when you have multiple layers, then you can increase the data width. Once the data width is increased, then without increasing the clock rate, okay, without increasing the clock rate, the bandwidth can be increased, because within one clock cycle, okay, so much of data is getting transferred. So we get the peak performance, peak bandwidth without increasing the frequency of the interconnect. So that can be achieved. So AMBA promotes design reuse by defining common interface standard for SOC mode. So this is a very important. Again, I am reiterating that it is a common interface standard for SOC mode. Okay, good. So before we get into the some bus cycles and their interfaces, let us see what are the conventions. This all of us are clear, and wherever there is a gray area, the value of the bus, either it's 1 or 0, is not defined. Okay, when there is a transient glitch in the bus, it will be interpreted like this, which is expected. Okay, and then when a bus from either from high or low is becoming a high, becoming a high, this is the signal. When the bus is shown like this, okay, particular timing, okay, this is all at particular time t. So the value could be 1 or 0, but it is a stable state. Okay, it is completely stable, driven properly. And high impedance state, that means this is a very important property of supporting a low power design, because once the bus is on high impedance, nobody is driving the bus, so it is not drawing the current, and its capacity effect on the circuitry on the system is also less. So high impedance state is shown like this, and any change in the signal is shown by this particular thing. And when it is coming from high impedance to stable state, it will be changing, okay, for a moment, and then it becomes stable like this. Okay, these are the different signals. Shaded bus and signal areas are undefined. The bus or signal can assume any value within the shaded area. Okay, it could be 0 or 1, or it could be some intermediate values. Okay, no, we don't bother about no module which is connected to the bus will be sampling at this time. So it is safe. There is nothing. No other module will go read or anything corrupted data during this time. The actual level is unimportant and does not affect normal operation. That's what I'm saying. It does not affect the normal operation of any of the 6 modules connected to the bus. Okay, let us now see a overview of the bus. Okay, let us look at some more details about AMBA. So it was introduced in 1997. AMBA has got 2 levels of hierarchy. I have already told you this. Okay. Okay, advanced high performance bus or AHB. So this is one level. Okay. Another one is advanced peripheral bus. So now I am giving you some more. The AMBA is a standard architecture, that is a microcontroller bus architecture. Under that, different bus standards are there. Okay. So either AHB or AHB will be in a system, and ACB will be there. I will give you I'll show you a diagram where you will understand what is this peripheral bus. This is for a low power, low performance, okay, peripherals to be connected. And when a low performance bus is connected to peripherals are connected to directly, if they are connected to the high performance bus, because of the delay of the peripherals in the system, the performance of the high performance bus or the transactions on this bus by high performing modules like processors and memory. Okay, memory is not high performing, but at least which has got a very good access time. Those will be delayed because of the presence of this. So that's why they have divided this. So low performance and low power devices, not only low power, actually low performance peripherals, which are slow peripherals, are not connected to the high performance bus. That way, because of the low speed peripherals, the high performance bus and the modules connected to them are not slowed down. Okay, that's the purpose of 2 levels. On-chip test structure, that is very important, which I mentioned, built-in structure for testing modules connected on the bus. So this helps in time to market. And a minimum of 32-bit data operation is recommended in the standard, and it is extendable to 1024 bits. Okay, minimum of 32-bit is recommended, but 8-bit also you can provide 8-bit data bus. Okay, so this is the high-level overview of AMBA. Now let us just I'll tell you what are the some ideas on high performance bus. Okay. Here, okay, so in this AHB bus, okay, the AMBA AHB is a high performance, high clock frequency system modules. Okay, high clock frequency system modules are connected to the bus. AHB acts as a high performance system backbone bus. Okay, this is the bus which is used for connecting high performance and high clock frequency system modules. AHB supports efficient connection of processors, on-chip memories, and off-chip external memory interfaces. So the different processors in the system SOC. When I say system, it's SOC. Okay, because these buses are going to be inside the SOC. So if you have a multi-processor, and this is actually supports multiple masters in the system. So AHB supports multiple masters, so you can have multiple processors in them, and they are all connected to the AHB bus. And on-chip as well as off-chip memories are connected. External memory also connected to the same AHB bus with low power peripheral macro cell function. So this low power peripheral macro cell function also there, but may not be connected directly. It could be through APB bridge that I will talk about later. AHB is also specified to ensure ease of use in an efficient design flow using synthesis and automated test techniques. So it also has easier design flow so that you will be able to integrate the modules, different peripherals or different processors or memories in the SoC. Now, what is ASB? Okay, Advanced System Bus. The AMBA ASB is for high performance system modules. Okay, actually this is either AHB will be there, okay, in a system high performance bus, or if we don't want in a system where this kind of a high performance system is needed because this complexity is more and power consumption will be more, and it is meant for a high clock rate peripherals, high clock rate processors. But if that much of complexity is not needed, then a designer can choose an ASB there instead of ASB, either this or this, okay, any one of them. So AMBA ASB is an alternative system but suitable for use where the high performance features of ASB are not required, and ASB also supports efficient connection of processors, config memory and others. So whatever AHB supports, ASB also supports, but this is meant for a low performance systems. So naturally it will area requirement will be less compared to this, complexity will be less here, and power consumption also will be less. So this is a designer choice whether they use AHB or ASB. What is APB? It's advanced peripheral bus. AMBA APB is a low power peripheral. It's for low power peripherals. It's optimized for minimal power consumption and reduced interface complexity to support peripheral functions. So the interface is simpler, it's not complex design, and minimum power consumption. APB can be used in conjunction with either version of AHB or ASB. So APB can be used along with either of this. Okay, as I told you, so processors and memories will be using these buses. That means they will be residing on this bus, and all low power peripherals will be on APB. So they can be APB could be used along with this or this. A compatible bridge, either AHB to APB or ASB to APB module is used for connecting the APB. So there should be a bridge. As I told you, a high performance bus cannot be connected to a low performance bus directly. So there should be a bridge. I will tell you why it is required and how it helps in satisfying both the requirements. Okay, let us hold on. Now before that, let me give just a small overview of what is a macro cell. Okay, those who are not from design background will be able to appreciate this. So a ASIC is a chip which is built custom made for a particular application. Okay, the name clearly mentions that application specific integrated circuit chip. So a macro cell array is an approach to the design and manufacture of ASIC. Okay, it's one way of doing things. Maybe not a complete ASIC, maybe a part of it. So essentially it is a small step up from the other similar gate array design. Okay, gate array, if you are aware, it will be provided with a different gate. Okay, and then maybe more NAND and NOR gate will be there. Okay, and then of course some buffers and inverters and all that. So these kind of generic gates will be provided, and then they will be connected according to the circuit requirement. So you may realize any circuit using different generic gates, or maybe a specific NAND and NOR gates, or generic gates, but we could use other gates also to implement a final system, a circuitry, which is a gate array. Rather than prefabricated array of simple logic gates, the macro cell array, okay, is prefabricated array of higher level logic functions. That means instead of designing, having an array of simple logic gates, it is a prefabricated high level logic, which are flip flops or ALU functions or registers and like. So bigger registers may be there, and then maybe flip flops will be there. Okay, so this kind of thing maybe okay are ALU functions. Okay, so multiple, maybe not one or two, multiple will be there, and then how they are connected is what is decided during the later stages. Okay, so macro cell enables in building such a solution with the basic functions which are high level logic. These logic functions are simply placed at regular predefined positions and manufactured on a base. A standard cell library is also sometimes called as macro cell library. So later on they are interconnected to realize the final functionality that is required. Okay, this is just to give you an overview of what is a macro cell. Fine. Now typical AMBA based microcontroller. Before we go into the detail of each of the bus and how bus transaction happen, let me tell you a typical implementation of that. This is one SoC, okay, which is having both AHB or ASB bus and APB bus, and it has got a bridge between the high performance bus and a low performance bus. And what are these devices? They are all devices which have got very low bandwidth bandwidth devices. Meaning the data generated by these devices are all comparatively very low rate. Okay, very low rate. You can imagine how many key entries can be generated from a keyboard. It's basically our limitation on how many keys that we can press. And this may be different. Maybe it could go up to few kilo baud rates, but still it is not as big as gigabyte range of transaction that happen over this bus. So here there are few bytes or maybe kilobytes of data. Here few gigabytes of data transfer per second, of course. Okay, so you can see the difference between these two. I don't know, almost around 10 power 6. So that's why the bridge is coming in. Let me, this is the right time, maybe I can design, now I can tell you something about what the functionality of a bridge here. So suppose if any of the processor, okay, this is the ARM processor, and then there is an on chip RAM, and then a DMA, and external bus interface memory. So external memory is connected to this interface. So this could be a master, and this could become a master, and of course this will be a slave memory, and this will be a slave in the AHB bus or ASB bus. Now this master, okay, master is the one which initiates transaction on the bus, and slave responds with the whatever the master asks for. Now this master could communicate to a peripheral also. So you might have written some code or maybe a device driver interface with the connecting to the UART. So the ARM processor is talking to the peripheral, means or you are trying to write one character into the bus, into this particular register, which needs to be UART will be connected to a PC maybe. Okay, let us assume this is a PC is there. FTXD, RSD. Okay, these are all transmit and receive. Okay, data flows in this way and data flows here. So characters will be sent over the serial bus. Okay, some baud rate, maybe 9600 baud rate to 11.11 kilo. So 9600 is a standard. Maybe we can say that this is a baud rate. So every character may be generated by this processor, and then it is writing into the UART. Now what happens? UART is a very slow device. So connecting to that, if it waits for UART to give back acknowledgement, it will be unnecessarily holding this bus for long, which is meant for a few gigabytes of transfer. So it is not worthwhile to make this bus wait for some transaction over with the low performance devices, low data rate devices. So to remove that particular delay in in interfacing with the or talking to these devices, there is a bridge here. So which is actually helps in buffering the data which is coming from either here or in this direction, and then completing the remaining transaction. So the ARM processor, if it wants to write into the UART, it writes into this, and then bridge says that okay, I will take care of this talking to the UART, so you can go ahead with the transaction. So the transaction gets completed here, and it can communicate with the bus memory, or it can talk to this, or it can indicate some DMA with the memory, whatever it can do. So this bus is freed up for the next transfer, while this bridge is helping in terms of completing the previous transfer that ARM has initiated. So that's the job of a bridge. Okay. So ATB bridge is always connected to the AHB or AHB through a bridge, so that it doesn't impact the performance of this bus. Okay, I hope this is clear to you. Let me tell you what each bus features are. High performance, of course. Pipelined operation. What I mean by pipelined is when an address transaction happens. Okay, with the bus transaction, actually you can split it into multiple things. So address and data. Okay, suppose if it is a read cycle, address will be generated. After some time, the data will come from memory. So in a pipelined operation, while address is generated for the previous cycle and the data is yet to come, another address generation could happen. Okay, the transfer for another transaction, that something to do with we can overlap the operations. That's basically typical to pipeline in the instruction, where one instruction will be in a fetch stage and another instruction will be in a decode stage and another one will be in execute stage. The bus transactions also can be in different stages. So that is called pipelined operation. So because of that, the efficiency of the bus is improved. So the bus is not idling at any time, waiting for some memory to respond. Some other transaction can be initiated. For example, suppose ARM wants to write something into this bus or read from this memory. It will take some time for it to respond back with the data. By the time, maybe DMA can initiate some transaction with this external bus. So address can be put here, and it will be resolving that address for it to write something from maybe from RAM to external RAM, or from some other peripheral here connected, another processor here. So or some other memory, okay, from memory to or peripheral to memory, whatever it is. So when multiple transactions happen, it could be pipelined. So that's what is the advantage of the AHB bus. Okay, sorry. So multiple masters could be there. So another processor can be there. So this could be a master, or ARM could be a master, or DMA also could be a master. Burst transfers are possible. That means one ARM sequential cycle followed by multiple sequential cycles. Split transaction is possible. Multiple transactions can be split and they can be executed. So effectively the idling time of the bus is minimized. Okay, that is the features of AHB. AHB, similar thing to, you see this, only these two are not there in the AHB because it is a complexity is less and it's for low performance devices where you don't want the complexity of AHB, then we can go in for AHB. Okay. Now what is APB? Advanced Peripheral Bus, which is a low power, latched address and control, simple interface and suitable for many purposes. So now you can give multiple peripherals can be connected here. Okay, because of the latched address control. Very good. So now let us go into some more details of AHB. This is a typical bus transfer of AHB bus. You see here everything is appended with H to say it is AHB signals. Okay, and H clock is similar to M clock we saw. Okay, main clock in the ARM. H clock is for the AHB bus, the main clock. So initially it is address phase and then the data phase in the clock. So address is put here. Assume that it's a read data. Okay, so write data, it could be this is showing you write data, what is happening, and the read data. Okay, and here what is assumed is data width of 32 bits. Okay, it could be, as I told you, it could be varying from 8 to 1024 bits. So In a transaction, you can transfer 1024 also bits also in one transaction, but the recommended is 32 bit. And then what happens is during this address phase, address is given, okay, and then the write data is available in the data phase. When after this HDD, okay, by the memory, if the processor, this is coming from processor, suppose this is coming from some memory, sorry, master, it could be a ARM processor, okay, it wants to transact over the bus with a memory. So slave is a memory, correct? So it wants to write the data into the memory. So the memory has to tell whether it is ready to accept the data by HDD is a positive value. So when it becomes high, it means that it is ready to accept the data. So when this is made high, then the data is put. Now suppose in this clock cycle also, if this continues to be low, what will happen? That is called the wait space. Because the memory wants to add more wait space because it is still yet to decode the address, or the memory is a slow device. It is a low performance memory. So in that case, it can put some wait states by extending this. It will not make it high, and then it will delay the transaction. So the master ARM has to wait for making data available until this goes high. Once this goes high in this side, okay, clock cycle, then when it becomes low, the data is made available and the memory can fetch that during this time. It will take the data which is available on the bus, and then it will bring down this value. So if it happens to be sequential access, maybe it will continue to hold it, and then it will read the other data that I will show you later. And what about this? This is for reading the data. So when it says that I am ready to provide the data, then the master can read the data from here. So it is showing a write data from master to slave. This is a reading a data from slave by master. Okay. So the data will be available when the HDD, the ready from slave, is made high. I hope this is clear to you, this particular answer. Now it's mentioned that there is a centralized arbiter in the bus. Why is it required? Because multiple masters are supported in the AHB bus, there should be an arbiter. If there was only one master in the system, then there is no need for an arbiter. This is only what's going to be initiating any transfer. So this master is in control of the bus, and it doesn't have to worry if anybody is using the bus or not. But once there are multiple masters in the bus, then everyone needs to make sure that the bus is free for the master to transact over the bus. So unless otherwise there is somebody who is centralized and looking at the transaction happening over the bus, the individual masters may not be aware of what is going on. So that is why the centralized arbiter takes care of giving access to the bus. Okay, so it can even associate some master as a default master. That means if nobody else is asking for the bus, the default master will be given the control of the bus. So the default master will be, suppose this is the ARM processor, maybe we can make it as a default master that is configurable. So if no one else wants a bus, this will be given. Otherwise, there will be a priority, and then accordingly the arbiter decides about who will be having the control of the bus at any particular point in time. So this kind of what all the interfaces with the arbiter and the master. There is a bus request coming to the arbiter. Okay, bus request coming from the master to the arbiter, and a grant going. Okay, grant going to the particular master. So how many such lines will be there? With every master, there will be a request and grant connection. Okay, one will be in this direction, one will be in this direction. Okay, request and grant. So arbiter gets all the requests from everybody, every master in the system, and then it chooses one of them based on some priority. Okay, and then gives access to one of the masters. So grant will be only one. Maybe it has chosen this, then only one master will get the grant, and then the master will drive the address or data based on whether it is a write cycle or maybe it will wait for the data if it is a read cycle. So this is how the AHB bus, okay, connected to by different masters communicate over it with the different slaves in the system. So what is the order? Before any master wants to transact over the bus, they need to get the permission from the arbiter, which is a centralized arbiter. Looking at all the requests coming, so all the masters should be connected to the arbiter, like I just showed here, and then they will be granted bus at a particular time. So what happens? One of them will be based on the choice. One of the address coming from any one of the master will be going to the bus, and then based on the choice, again the data driven by any of the slaves will be going to the particular master. Okay, only one will be driving anyway, one of the slaves, because based on the address, one of the slaves will respond, and then it will be given to the particular master, and this multiplexer takes care of choosing the particular master based on the grant given by the arbiter. And then what happens? The decoder, the data coming is decoded, and then it is given to the particular master. Okay, read data max. So this is how the interface is between the set of slaves and the set of masters in the AHB bus. Okay, I hope this is clear to you. So AMBA AHB bus protocol is designed to implement a multi-master system. Unlike bus architecture designed for TCP based systems, the AMBA AHB bus avoids tri-state implementation. It avoids tri-state implementation, where it is not a PCB based system. Okay, the bus is not going to be on the PCB; it is going to be on the inside the chip. It employs central multiplexer interconnect scheme. Okay, so it is not the other devices need not have to be in a tri-state condition because there is a mux in the system. It provides high performance and low power than using tri-state buffer. So because of that, the performance is better and the low power also is achieved. Because if it is tri-state, every device needs to drive the bus. It will take some time for charging the bus. Because of the capacitive effect, there will be the time taken for the signals to stabilize on the bus will be longer. Okay, in a typical tri-state system. Whereas if it is a mux-based system, everything is actually connected, but power may be a problem. But the thing is, it will be easier in terms of achieving the proper performance, and it is a low power than using the tri-state buffer. Okay, because there is not too many charging or recharging, discharging of the buses. So because of that, the power dissipator or buffer power consumed by the buses or the signal over the buses will be minimized. The transactions are less. Okay, if number of transactions over the bus is reduced, then the power consumption will be less. All bus masters assert the address and control signals indicating the type of transfer each master requires, and then central arbiter determines which master has its address and control signal routed to all the slaves. So arbiter determines or chooses the particular master. Okay, it grants the bus for a particular master, then that master's address and the control signal. What is the control signal? That is control signal talks about whether it is a read or write, whether what is the width of the transfer, whether it is half word transfer or a full word transfer. Okay, or maybe a byte transfer. So this kind of different things can be communicated over the bus. A central decoder circuit selects the appropriate read data and response acknowledge signal from the slave that is involved in the transaction. So particular responding data coming from a slave device has to be connected to the master who is holding the bus. So maybe who has initiated the transaction. So that master will get the data coming from the slave. I hope this is clear to you. Now data transfer is a pipelined or tenured bus. So address phase of any transfer can occur during data phase of previous transfer. So it's overlapping. Address and data phases, of different transactions are overlapped. This is what is called pipelined or tenured bus. Because of this overlap, performance of the bus is improved. Okay. Now what is a retry? Suppose one transaction, suppose it has got a non-sequential address. First address is non-sequential, and then the remaining addresses are sequential. That means once this transaction is done, then the next address could be then +4 maybe, based on the 32-bit or whatever database. So that is what is +4 is shown. Okay. So this is indicating whether what type of transaction is happening, non-sequential or sequential. Okay. And then why is it idling now? It is idle signal is generated when the slave responds with a retry, or it says that HDD is low. That means after this transaction was completed, okay, HDD is low. That means the peripheral or the slave device has said that I am not ready to accept the next transaction. So because of that, okay, there is a retry. That means the data what was initially given, okay, the address and the data what was given is not maybe written into the memory properly. Maybe there was some problem. Maybe there was a corruption in the data, because there may be a parity check could be there, and then maybe because of glitches on the bus, the data could be corrupted, and in that case, the memory device can initiate a retry. That means the same data is again addressed and data may be put on the bus for that to be accepted by the slave device. So I'm giving a retry example here. And then bus transfer. You can have a multiple transaction for a first non-sequential access. So different addresses are given now, as you see that. Okay. And if you see, there is a bus transfer, that signal is sent. That means it is communicated to the devices that the bus transfer is happening, and then the different data for a specific those addresses are given on the bus. Okay. So they are all provided. Again, you see here it was ready in this case, and then it became low, and then it becomes continue to be high. That means it is ready to accept the data continuously. So because of that becoming low, you see this 38 is coming again. Okay, it is kept for long, and then this data is coming here. Okay, this address is given. This is delay actually, and then because of that, you see that this transaction is also taking more cycles. After that, the cycles are 1 clock only. This is taking 2 clock cycle because this device, a slave device, has said that I am not ready to take that particular transaction, because initially the non-sequential cycle takes more time. After that, the rest of the accesses will be faster. So sequential clock cycle, that's why non-sequential accesses will get more time, and it takes more time, and then sequential accesses becomes faster later on. So it starts accepting all the data coming later on. So this is one typical example of the signal transaction. If you are not able to follow this, please pause it for a while and then understand the sequence, because this is very important to understand how the different signals are helping in terms of transacting over the bus. Now, what is a split transfer? Now, what happens is during one transfer, okay, a grand signal is withdrawn, okay, and then for a slave signal to split, and then alter changes the grand. Okay. Now new master drives that. That means once the slave says that, see, one master is communicating, and let me explain. One master is communicating with one slave. Okay, maybe call it as M1 and S1. Now S1 says that slave signals a split transaction. I like to have this transaction to be split. That means this transaction bus cycle is terminated for intermittently, and then during that time the arbiter could give the bus to another transaction between a master and a slave. So new master drives that. So that's why you see that another non-sequential address is happening. In between there is an idle cycle, because the arbiter takes some time to grant the particular master, and then the master has to drive the bus. So this cycle is used for arbiter to choose another master and then communicate to the master, so that the other master, there should be something pending. Okay, some grant request is pending, so that arbiter could give a new master to use the bus, and then it is generating another address. This is coming from another different master and a different control signals, and that transaction happens. So the split transaction is communicated for breaking a transaction happening, and then the arbiter decides and then gives the control to the bus to some other master. So this is one typical example of that. So what are the bus bit scenarios? One way to improve bus bit without increasing the frequency of operation is to make the data path of the on-chip bus wider. So this is possible. I told you this. However, it is recommended that a minimum of 32 is used or maximum of 256, because even increasing the bus width to this is a little bit, though it improves the performance, there is a stability, reliability issue might be there. So they are recommended with this 32 and 256. For both read and write transfers, the receiving module must select the data from the correct byte lane on the bus. So as earlier, if you remember, if byte transfer is happening, maybe a particular odd address or even address, a particular word, a byte. Sorry, this is the word. Okay, these are all bytes. Okay, if suppose it is writing only this byte, so maybe the same value can be driven on all the buses. Okay, and then I was saying earlier that based on the memory which is there, it could take this value and then internally it can write into a particular location in the memory. But this actually driving the same data over the multiple buses actually increases the power consumption. So in this case, in the AHB, the correct byte lane on the bus needs to be driven. We don't have to replicate the data on all the byte lanes. Okay. So the module must select the data from the correct byte lane. So any peripheral or a slave connected to the AHB bus should be capable of getting the byte specifically based on the address. Which byte lane has to be used for reading the data. This slave device should be aware of, and then it should do it accordingly, either reading or writing. Okay. Replication of data across all bytes lane is not required. Okay, now let us touch upon simple, a small introduction to APB. So APB has three states. One is idle state, and setup state, and enable state. Okay, so these are the signals. It will be in idle state where nobody is driving the bus. Okay, no power is drawn, and it is all the devices are not transacting over the bus. And then if anyone wants to drive on the bus, then it gets into setup phase, and then based on the transfer, whether multiple transaction happens, then it will be in enable and then setup phase. It will go into this. If no transfer is there, then the state of the bus goes to idle state. Okay, this is a kind of a state transition, and this is a select. A particular peripheral device will be selected if it is one. Okay, and then that will be enabled to transact over the bus. So here, if you see, all the signals are appended with a P. That means it shows that it is a APB bus signal, whereas AHB signals were given H as a prefix. Now APB states, idle state, the default state for the peripheral bus setup. When a transfer is required, the bus moves into the setup state. Where appropriate, the select signal is asserted. Only one will be asserted. Okay, and then the bus only remains in the setup state for one clock cycle, and will always move to the enable state on the next rising edge of the clock. So once it is set up, it is actually one particular device in the APB bus. Peripheral is selected, then it will be in a setup phase. Afterwards, it will be in the enable phase. So that peripheral will be either reading or writing to the bus. So in enable state, what happens? The enable signal P enable is asserted, and the address write select signal remains stable during the transition from setup to enable. So either write or select signal will be active during that time. So this is a typical transaction over the APB bus. This is a clock. This is actually a low. No, it's not a low frequency clock. So address is given. Okay, it is valid here, and then the write signal is given. That is, it is writing into this address with a particular data. Okay, and then a particular peripheral is selected and then enabled. So this is the from ideal state it enters. Wait a minute. Okay. Okay. So okay, yeah. So what happens? It is in the ideal state here, and then it enters the setup phase and then enable state. Once it is enabled, it is in the enable state. So this is a setup state. Setup. This is enable state. Okay, and then this is the idle state. So now you may wonder, why is this address and the write signal continue to be high? Why are they not driven low? In order to reduce power consumption, the address signal and the write signal will not change after transfer until the next address occurs. See, as I told you, when there is not much of signal transitions, then the power consumption will be reduced. So to keep that, and it is not right stated, as you remember, this is not right stated bus. So the peripherals need not be taken off from the bus, or the bus need not be right stated. So the address signal will remain. Address, whatever the earlier cycle, whatever the address put on the bus, it will continue to be there on the bus until the next select is happening, and then the next address is put. Till then there will be same address and write signal will be maintained. So that is a retransfer. This is a write transfer. This is a retransfer. So the data comes in late. Okay. So the device is selected and then enable, and the data is driven by the peripheral device. Okay. Master reads from the slave. Retransfer. I hope this is clear to you. Very simple. So APP bridge. So this is the kind of a APP bridge which I mentioned. So all the the P data and the rest, all these are connected to this. Okay, and then the system bus to the system bus, either it could be ASB or AHB. Okay, this particular APB bridge looks like a slave. Okay, so that's why the slave interface is connected. So the AHB bus or AHB bus will be on this side connected to this. So we are not showing any of the stick signals here. Okay, they are all here. So it is from the AHB bus perspective, this is one of the slave devices, and then rest of the signal are all on the APB bus side. So APB bridge is the only bus master on the AMBA APB. Okay, so AMBA APB bridge is the only bus master. In addition, the APB bridge is also a slave on the higher level system bus. So on the APB side, the bridge is the master. Okay. This is what is going to actually mimic any transaction happening between the devices on AHB side to the APB peripheral. So actually this is the master as far as APB is concerned. Sorry, APB. On the APB bus, the APB bridge is the master, whereas on the AHB side, this is the slave. So this is AHB side. Okay, though the signals are all from APB. And this is the APB side. Suppose if you take, it behaves like a master on this side and behaves like a slave on this side. So whatever data is coming from AHB is buffered here and then later on delivered by choosing a particular one of the devices, slave devices, and then generating this. The address would have come from this, right? So it will, based on this address, it will know which particular device is selected, and then it drives the same address here, maybe modified a little bit if it is required, and then the particular peripheral device will be selected, and the data what was given, suppose if it was a write, the data is already buffered and address is also buffered. Both will be driving here. So by the time this master who was actually originally driving this would have gone into completed the transaction, and some other transaction may be happening on the AHB side, whereas this is still going on the APB side. That's what is the advantage of having a bridge. So with this, we have come to the end of this session, which talked about all the AMBA architecture. This is the very high level overview of these buses. Okay, and I think with this introduction, if you can read based on your intent or based on what you are trying to design or build, either as a hardware designer or as a embedded software developer, you should be able to read through all the manuals of the different buses and understand more details about how certain things need to be interpreted. Okay, in a SOC. Okay, so I'm very happy to share this with you. I hope it was useful to you, and see you in the next lecture. Maybe looking at some of the peripherals. So we will be talking about some peripherals in the next lecture. Okay. Have a nice day. Thank you very much for your attention. Bye bye.